So next, I think I now have the privilege to introduce today's plenary speaker, Professor Frances Ross. She's a professor in the Department of Material Science and Engineering at Massachusetts Institute of Technology in Cambridge, Massachusetts. She received her undergraduate in physics and PhD in material science from the other Cambridge, Cambridge University in the UK, where she first became captivated by electron microscopy. She continued this interest during her postdoc at the AT&T Bell Laboratories as a staff scientist at the National Center for Electron Microscopy at Lawrence Berkeley National Laboratory, and as a research staff member at the IBM T.J. Watson Research Center. Her current research is based on the development of in situ electron microscopy techniques to help understand crystal growth, epitaxy and self-assembly, and electrochemical and other liquid phase processes. And on a more personal note, she is a extremely kind and generous person. And it's such a thrill to be able to work with her. So Frances, you have the floor.
Oh, okay, well, thanks Aubrey, Terza, Stephanie, for the opportunity to talk here, the invitation. I really appreciate it. I'm going to go straight to a slide since, let's see. Since that's more fun than looking at me, let's make it go.
Impressive office, Frances.
Oh yeah, compared to the last one, this is great. Yeah. Right, so I'm going to put this up now. I can't see now anyone else, right? So if you have questions, you have to speak up, or maybe one of the moderators can relay them, because I don't see it now on my screen. So again, thanks for the opportunity. I mean, it's what a great event it is, and very happy to be here and talking to everyone. So what I'd like to do in my time slot here is talk a little bit about in situ microscopy, what kind of things we can learn from it, but also Aubrey suggested some kind of sort of personal view of how I got to where I am now. So I'm going to throw in a few like reminiscences. Hopefully won't be too uninteresting, but let's see how it goes. So at least with this audience, we don't have to really emphasize either the joys of microscopy or the definition of in situ microscopy, but instead I just want to show some examples of things that we really enjoy doing. So this first video, which I hope shows as playing, come on, get on with it. Okay, so the first video shows a catalyst doing its job. So it's a liquid droplet, gold silicon eutectic liquid on top of a silicon post. And what you can see on the surface is a crystalline layer. So the interior is amorphous and the surface is crystalline. You can see some lattice fringes inside the liquid part, but in fact, that's the surface part wrapping around. So we're looking at a catalyst under the operating conditions, and it should be pretty clear that if you cool it down, take out the gas, take an ex situ image, you don't really get the full view of what was going on during the reaction. So in situ microscopy, where we operate some object, we expose it to its real working conditions. This is an essential way of understanding what's going on, especially in nanoscale systems, which are the most interesting ones. Right. So in the next movie, I'm showing some gold triangles. They're resting on a sheet of graphene, and we're slowly warming them up. And what you can see is that they are moving around. I know the frame's moving too, but the particles themselves are moving. Look at the bottom one, it's going to rotate in a moment. Yes, there we go. So they're at their equilibrium wolf shape sitting on the surface. They have very weak bonding to the graphene layer, and we'll talk about that a little bit more later on. And finally, I want to show a liquid phase video. These are bubbles of hydrogen being nucleated and growing and coalescing in a thin layer of water that's trapped between two silicon nitride windows. So obviously bubbles are extremely important in processes like catalysis, cavitation, corrosion, and the ability to see them at nano kind of scales is really helpful in understanding how they form. So what you can see in these three images, they're all transmission electron microscopy, but they're at very different length scales. And so even without atomic resolution, having the time resolution is essential in understanding what processes take, how processes take place. So when I have to discuss why I'm interested in this kind of thing, and I think of, well, you know, what it's intrinsically interesting, right, to see things like this going on, but we have to have a motivation really to help us decide what to look at. And so here's a slide that shows a kind of summary of what the overarching theme is when we do these kinds of experiments. We're trying to address a grand challenge in material science, which is, can we design and build materials that have specific useful properties, which could be anything, structural, electronic, magnetic, optical, whatever it might be, using the tools of nanoscience. Nanoscience is extremely helpful because shrinking the size of a material often unlocks new properties. So we need to create nanoscale materials with very well defined structure. And so obviously one approach is shown here in this first image. You can move each atom into place. This is the world's smallest magnetic bit, at least it was in 2012. I don't think it's possible to beat this. 12 atoms of iron that have been assembled by a scanning probe microscope into a little bit, and you can see they're coded by the spin direction in the atoms. So this is amazing, but it's also not practical for real life applications. So instead, we want to use a self-assembly process. We want to have something happen spontaneously that creates many objects all at once, but self-assembly typically creates rather simple structures like hemispherical raindrops. Instead, can we use simple self-assembly processes to build much more complicated structures with different components and elements and compositions that we specify? And so we need to trigger a process to happen spontaneously. In order to make this work, we need to control the process, and therefore we need to understand it. So we obviously need to use microscopy to even see the things that we're trying to create. And so the question is, to what extent can electron microscopy help in this overarching goal of solving this grand challenge in material science? Okay, so let's stop here for a moment and say, well, this all sounds rather smooth. You know, she's giving like a corporate talk where she's expressing this kind of overarching theme for her work. But in real life, we all know that you don't get to these kinds of conclusions just like in one moment. It's really a kind of a career's worth of thinking about things and making decisions that get, or just letting things happen that gets you to the position that you're in and the way you think about things now. So what I want to do is just show a few of the things that I think have been important to me during my career, and some of the people I've worked with, to get to a position where we can then talk about some of these nanoscale processes, which I'll do a bit later on. So I want to start by showing you a page from my thesis, and this is the start of my pathway into electron microscopy. I did my PhD with Mike Stobbs at Cambridge. Some of you may have heard of the Stobbs factor, which is the difference between the intensity that structure should have in a simulated TEM image and what you see experimentally. And Mike Stobbs was obsessed with this. He was really keen to understand the quantitative features of his microscopy data rather than just looking at the pattern of the dots or the stripes and saying, oh yeah, this must be the case. So he was an inspiring person to work with. In those days, we had to print the images from our thesis in the darkroom and glue them onto paper. So it gave us the scope to do things like this, but it really took quite a long time. So appreciate that next time you compose your figures in Adobe Illustrator or whatever it is. So this is how it used to be done a while back. Now, I did my postdoc at Bell Labs in Murray Hill, New Jersey, and I worked with Murray Gibson, a very wonderful person to work with. And again, things have changed a bit. We wanted to do silicon oxidation. We oxidized silicon in a microscope adapted for UHV operation so that you could clean the silicon surface, have it really clean, and then introduce controlled amounts of oxygen or water vapor at a particular temperature and record the results. So these images use the forbidden reflection mode, which is one of the diffraction spots that does not exist for an integral number of unit cells, but it does if you have a fraction. So you can follow steps on the surface as you oxidize. And we recorded onto this reel-to-reel tape, and it was expensive. So we had 60 minutes. And then when it was over, we had to find another tape, and then we had to delete the first one once we'd copied it over. So it was kind of tiresome, but that was the way it was done at the time. And so when I moved from my postdoc, I went to the National Center for Electron Microscopy, and I recommend to anyone thinking about this stage in your career, the user facilities give you such an insight into experiments. A lot of people come through the doors, and I learned from my advisor, Uli Darman, the head of NCEM at the time, all of them have some kind of a merit. You know, all of our visitors give us pleasure, you know, some when they arrive and some when they leave. But working with users helps you really appreciate everybody's interests and to see whether experiments are worth doing, if they're going to be interesting, or whether it's better approached using a different technique. So at the time we had our own research programs, and this one, these images are from an early liquid cell development project where we were trying to get anodic etching of silicon using HF electrolyte through a layer of conductive silicon that was embedded between two intrinsic layers. So an interesting project that actually completely failed, I would say, but was still fun to try out. So after being at Berkeley, I somehow moved from California to New York in the middle of winter. I don't know how that happened, but I had such a wonderful time at IBM working with Ruud Tromp and Mark Reuter, and I learned how important the technical aspects are in terms of designing and building equipment that does a certain function. We looked at things like the growth of germanium on silicon in the microscope. So this movie shows germanium quantum dots spontaneously forming on a silicon surface. They're showing up because of their strain contrast. And if you look at the small ones, you see that the little ones disappear and the big ones keep growing. And this is while we're still adding flux. So the small ones are shrinking even though the flux continues to flow during the experiment. So this is clearly a process of Ostwald ripening where we can exchange. So germanium comes down from the gas phase, supplied as digermane. It lands on the surface. It diffuses across the surface and it joins an island, but it can also leave an island, and so the smaller ones with higher energy per atom disappear at the expense. You know, the material goes to join onto the larger ones. At IBM, we also got very interested in developing techniques for looking at liquids in a way that would work better than the stuff I showed on the previous slide. So liquid cell development based on microfabrication, which turned out to be a much better approach to doing this in a realistic way. I'll talk a bit more about that, although that's not the focus of what I'd like to talk about for the rest of my time here. So talking about nanoscale processes that you can trigger in the electron microscope, we're naturally drawn towards nanowires because the process of forming nanowires was of great interest in microelectronics because it's a way to create small structures without using lithography. So the process works like is shown in this PowerPoint science slide. So we get a lot of this with nanoscience because often you don't have the image that goes with. So as you add your material, in this case silicon supplied as disilane, it lands on the surface of the sample. The sample is covered by droplets of gold silicon eutectic. You'll recognize that from the first slide. The gas decomposes, the silicon is left behind, and it attaches much more readily on the surface of the droplet. And so you get a supersaturation of silicon within the droplet that gets precipitated at the interface and therefore adds silicon layer by layer at the growth interface, forming a nanowire that just keeps growing and carrying its catalyst along with it. And this model was proposed in the 60s, but here we can verify it in the electron microscope and show that in fact the PowerPoint science really does express what's going on pretty accurately. So you can see a perfect prism of silicon is forming. Look at the thickness fringes here. You can see surface features. You can see the shape of the catalyst, the phase of the catalyst, the structure of the interface during growth. So, so this process was of great interest because of its potential for creating small structures. But again, as I said before, we want to understand the physics of this process if we're going to have a chance of using it in a real, manufacturing context. So let's consider a bit how it is that we're going to study this process and what we can hope to learn about it. So here's a photo of the microscope at IBM. Here's the microscope itself. It's been modified so that we can do these chemical vapor deposition processes in real time in the microscope. So you need an ultra high vacuum within the microscope that's achieved by some extra pumping. You need a delivery source for the gases, including some toxic nasty gases that you want to be really careful about handling. You need a sample insertion that can be compatible with UHV. So we have a disconnected sample cartridge that gets fed into the microscope and then can move to other locations within the vacuum system where we can clean it, calibrate the temperature, deposit material on it, etc. So the kinds of samples that work well for nanowires are these vertical samples. The electron beam passes across the face of a little block of silicon. The front side is the polished side. You put the catalytic particles on the front side. When the nanowires go out sideways, they're in a perfect geometry for getting good images of their structure and their kinetics. So having set up this equipment, let's see what we get when we do the experiment. So we can measure the properties we can measure the growth rate, the interface morphology, the phase of the catalyst, etc. during growth under calibrated conditions of pressure and temperature. So this movie that I'm going to show first, come on, let's do it, is a high-res image of a nanowire growing. This one actually recorded at Brookhaven using the environmental TEM. And you can see in the movie that the growth is taking place by little jumps, right? You see that the corner has little jumps and the motion of the growth interface has little jumps. Now, what if we cut out this section of the video and we expand it and we play it a bit slowly so that you can see how it goes. So here it goes. And did you see that? A single jump. And if we wait and wait and wait and wait, and there, another jump, another sheet of silicon atoms was added onto the growth interface. And it continues in this way as little jumps during the growth of the nanowire. We can also go other materials. How about gallium arsenide? So we flow trimethyl gallium and arsine with gold catalysts, and we get very different results. Look at the growth of these things. Do you see how the step is moving slowly at the interface, back and forth across the interface? And this very different growth kinetics can be used to derive some of the physics of what's going on. So without going into a whole lot of detail, I should just point out that we have a steady supply of the growth material. So silicon arrives at the catalyst at a steady rate, and it has to decide what to do. Supposing the catalyst has very low solubility for the growth species, then the silicon comes in, it's got nowhere to go, it lands immediately, it attaches onto the growth surface, and the steps move gradually across as the nanowire grows. Instead, if there's a high solubility for the growth species in the catalyst, it will easily remain in solution, but eventually the chemical potential of dissolved silicon will rise high enough that something has to give. It has to precipitate, and at the moment it nucleates step. Enough material is present to complete the whole step all at once. So you can see that you can relate the kinetics you see in the movies to the physical parameters of the materials that are involved in the nanoscale process. So we can look at this and say, oh yeah, this will help us understand things like, how do I grow a junction in a nanowire? For example, I want to grow some silicon, and then I want to grow some germanium, and then I want to grow some more silicon. How sharp will that junction be? Well, you can guess that it's going to be a lot sharper in the first case than in the second case, because we have such a reservoir of the growth material. And indeed, this is the case. Depending on the catalyst properties, you get very different interface sharpness when you grow heterostructures. But one of the fun things about doing in situ microscopy is the opportunity to see something that you completely didn't expect to happen at all. And so one of those things is shown on this slide. We thought to ourselves, let's go back and do this process, this PowerPoint science. I'm going to do it again, but instead of growing germanium, I'm going to grow some metal so that I make an electrical contact. Let's grow some nickel. We'll form nickel silicide. That will be a really good electrical contact for our nanowire. So we put the nickel in, and instead of growing a nice layer horizontally at the interface, we got this floating island. It doesn't really show up here, so I drew a boundary around it. But basically, this object forms, floats around for a bit, and eventually sticks onto the interface. And then you can continue the growth, and you see it here. Do you see it there? And this looks to me like an ice cube in a drink, right? So as you now grow some more silicon, you can embed the particle and end up with an isolated quantum dot within a nanowire. So you can see the richness that we get with these nanoscale processes that you could only really understand if you had seen them taking place in situ in the electron microscope. So I don't want to leave this topic with the impression that, oh yeah, everything works, you know, you plan it, you set it up, and then it works. There's all kinds of ways that the experiments fail. And so I'm showing a few of them here. If the vacuum is dirty, you get junk all over your sample, you can't grow anything. If the diffusion pathways get messed up, you get these odd shapes that are hard to use or understand. And you can also get kinking, growth instabilities, morphological changes, etc. And here's one of the most fun ones. We were very frustrated by this. Look, the small particles, they're growing. The nanowire is growing, but look, the catalyst is disappearing. And it took us a long while to realize that this is the same Ostwald ripening process I showed you earlier for germanium islands. The gold on the small droplet is diffusing down the nanowire, and it's going up and joining another larger droplet. So it provides a limit on the types of structures that you can grow. All right. So this type of work makes you think about other opportunities for controlling nanoscale structures that form spontaneously. And the last topic I want to talk about is work that started in IBM and is ongoing now at MIT. And it's really connected to the concepts of crystal growth that I showed for silicon and germanium. How does this all extend when we're talking about 2D materials? I mean, things like graphene or hexagonal boron nitride or molybdenum disulfide, which have sheets of atoms bonded strongly within the sheet, but each sheet is only bonded to its neighbors by weak van der Waals forces. So you can easily peel them apart, or if you could grow a single layer, it would be somewhat inert on its surface. And it could make all kinds of useful electronic or photonic devices. Some of them, one of them is shown here. If we can control these 2D materials, in particular, if we can make connections between a 2D material and the outside world, which of course is a 3D material. So what we have is we want to make the most use of 2D materials. We have to bond them reliably with the 3D world, but this is a challenge given the differences in the chemical bonding between the 2D and the 3D material. So how can we address this? And this is a great thing for the electron microscope, because we're trying to understand the relationship between crystals at the nanoscale, crystals that are very thin, and these make perfect TEM samples. Once you iron out some like technical difficulties, you can see right through them, and you can get information on the growth of materials of 3D materials on 2D materials. Right. So let's look at one of our favorite combinations: gold growing on molybdenum disulfide. And so these are actually ex situ images of gold on MOS2. You can see the MOS2 structure in between. You can see the shape of the gold islands. And what you can see most strikingly is a moiré pattern that reflects the difference in the repeat distance between the gold and the MOS2. So whenever we're looking at two crystals, in a column, one on top of the other one, the electron signal will respond to the alignment of those two crystals such that they go in and out of phase as you move across the sample. So this moiré pattern, we can analyze it to show that both the gold and the MOS2 are unstrained. There's no deformation of the gold because it's growing on this unmatched crystal substrate. It just grows completely happily, but it does talk to the MOS2 because you can see that each one of these islands has the identical orientation of its moiré pattern. So all of the lattices are aligned with each other, and the bonding is rather weak. You can see a little bit of jiggling just caused by the beam. The crystals are rotating very slightly, and the moiré pattern magnifies that rotation. Okay, so what can we do with this? Well, the first thing we could do is measure the spacing of the moiré pattern, and we already run into some trouble here because we get 1.8 nanometers in TEM between these spots. But when people do STM and they measure the electronic structure, they get a different period for the moiré pattern. So what is possibly going on with this? And again, we stared at it for a very long time and then worked out that the reason the two periods are different is because TEM is giving you a projection image. When you look through the sample, you're looking at the 3 layers of gold atoms within the gold crystal, the ABC stacking of the gold lattice structure. And if you don't care what height they're at, and you project this pattern on top of the MOS2 pattern, you get a moiré that looks like this with a 1.8 nanometer repeat distance. But if you care about the height of the gold, and you only think about the correlation between the bottommost layer and the 2D material, you find that indeed the repeat distance is larger because these sites on the moiré pattern are no longer equivalent. So it's hard to explain in a slide, something that took us like weeks and weeks to think about, but there you go. There is a reason for it, and TEM is giving us only a projection view of what's going on. And this difference is important electronically because the electronic modulation is really most sensitive to the lowest level of atoms and therefore follows the longer period, the 3.2 nanometer period. So 3D, 2D interfaces are exciting and you can control them, but you have to be a little cautious about analyzing the results from a TEM observation. So let's move along from gold to some other materials, and Thai gold is a very common contact material for conventional electronics. So how well does this work for the 2D materials? In other words, can we make nice Thai gold layers on a 2D material? And this would open up all kinds of opportunities if we could control the thickness and the size of the metal bilayer. And so this is what happens when we put Thai first onto graphene, and then we put gold on top. So in this first image, we put the Thai, we then put the gold, they align with each other. in a very beautiful epitaxial way. You can see the moiré pattern, you can see a rim of gold around the outside, and you can see every crystal is aligned with each other here. But if we expose the tie to a little bit of oxygen between depositing tie and depositing gold, you can see that the surface has been oxidized. The gold no longer sticks epitaxially, it makes little islands, and the quality of the interface is very different. So this emphasizes the importance of doing these experiments in a very well-controlled vacuum, and also when you're doing processing in microelectronics, of controlling the deposition conditions very carefully. What we can also get from these images is a sort of self-aligned golden tie by removing the gold from the outside of the triangle. Okay, so the last one I'll show you is bismuth, and I'm showing you this mostly because the image is so beautiful. The bismuth is growing epitaxially on MOS2, and you can see how the atoms line up after we deposit bismuth carefully and form an epitaxial, like a continuous but not, a connected but not complete layer, right? So if we want to broaden the possibilities of this, I've talked about growing metals on 2D materials, but how about we grow some other things? How about we grow germanium on a 2D material? Well, it doesn't work very well, but we know that gold works very well. And we also know that gold is a good catalyst to grow germanium nanowires. So if we combine these two ideas together, we get a movie, which is, I have to say, not my most exciting one, but look here. Do you see that little gray area that just appeared? And another one's going to appear just here. Wait for it, wait for it. There you go. So the gold is catalyzing the deposition of germanium. Because the gold is attached to the graphene and the germanium is attached to the gold, then the germanium has an epitaxial relationship to the graphene. So it's like a chain of epitaxy, a transfer of epitaxy, and we can do the same thing with silicon. We use silver as the catalyst, but we have to anchor the silver onto the graphene by using some gold. So now we have an even longer chain: graphene, gold, silver, and then silicon. So it may not be practical, but it's kind of fun to see all these crystal structures following each other in terms of their orientation. All right, so the last one I'll show you actually is a completely different kind of material, and a 2D magnet in which chromium atoms in the van der Waals sheets are lined up to make magnetic structure. And this has a very different symmetry. It has a rectangular unit cell, and we can grow other materials, like in this case, niobium trisulfide, onto the 2D CrsB structure to get epitaxy. And so I put this one up just because we've got two really bizarre structures. They're both very beautiful, and this just opens up so many possibilities for looking at 2D, 3D junctions and properties of the resulting stacks. Okay, so the last thing I want to do is just give a little bit of an outlook for these kinds of in situ growth experiments, because I feel like we're in a very exciting time for these kinds of experiments, and I want to just talk a little bit about what may happen next. So I think I've emphasized that you need to control the environment in order for these processes to work reliably and to get quantitative results out of them. We have to have a clean surface, we have to not have oxide, we have to not have contamination. If we achieve all those things, we can get very good epitaxy of materials that can be even quite difficult, like in this case, niobium deposited onto graphene, which gives fabulous epitaxy with these kinds of diffraction patterns. So we need an ultra-high vacuum environment in our microscope in order to do the growth experiments. But if you also have the ultra-high vacuum environment and the good control of the substrate, then this opens up other possibilities. If there are no random locations where things nucleate, then you can pattern nucleation sites And those will be the only places that are good for nucleation. So we can envisage experiments where we pattern our 2D material with maybe a fib or maybe the electron beam itself, and then do a nucleation experiment and control the position of the islands that grow. I haven't really talked about liquid cell microscopy in this much in this talk, but in this area for in situ microscopy for liquid cell as well, there's a lot of opportunities of improving the quantification of the data that we get out by understanding electron beam effects, by optimizing the resolution, by improving our ability to control the liquid environment within the sample. Okay, so I would like to conclude with a sort of optimistic perspective here. I feel like we're in a really exciting moment. We have really central developments in our imaging tools. We have higher resolution at lower kV, we have better detectors, we have MEMS technology, we have UHV environment for improving the control. So these developments in imaging tools can really be applied to accelerate our ongoing progress in discovery, use, and integration of new materials. In other words, helping us to explore a greater range of nanoscale materials reactions that can spontaneously lead to nanoscale structures with great complexity and useful properties. All right, so I'd like to finish by acknowledging a lot of people who contributed to the work that I have shown in the last half hour, and especially thank the funding agencies who've supported this all the way through. And I'll leave with one final picture of silicon bend contours, and I'll be very happy to answer any questions.
Thank you so much for the really wonderful talk. We have some questions submitted already, so I can go ahead and read them maybe to help. And I see lots of applause, also reactions from the participants. So the first was actually a comment. Someone commented on your first slide that they had never seen a crystal liquid interface before, and we're excited to see it. So the first question we will have here is, do you think it would be possible to image water droplets nucleating and turning into ice crystals on a super polished smooth metal surface?
I think you could. Obviously, you could use SEM if you could, depending on how small you need to see them as they nucleate. But in TEM, you can combine liquid cell technology with cooling technology. For example, to form humid air into droplets and later on into ice. And I think that given the advances in like low dose illumination, it may be possible to do that without melting it all with the electron beam. So it's something that hasn't been done in the TEM, but I think there's certainly engineering challenges, but I think there's a good chance that something like that would be able to be accomplished. For an arbitrary, of course, the sample in the liquid cell is microfabricated. The interior is usually just silicon nitride, but you can add stuff to it. So if it's like an industrial surface that you're interested in, that can be a little bit more of a challenge. But I can imagine there would be ways of doing that, even using the reflection mode that I showed for nanowire studies. So yeah, that's a great question, and I think there's a lot of opportunities there.
Oh, wonderful, thank you for the answer. And there's some people in the comments as well who pointed out that it seems like it could be challenging, but an interesting problem. So I received a question in a different direction as well. So you've had a whole bunch of different experiences from the UK to Bell Labs and at NSEM and R&D at IBM and now at MIT. And I'm wondering if you talk about career options and pathways and different, how these different institutions are different, and speak to that differences. So that's, I think, a good.
I could probably talk about that for hours, but I won't do that. I think the main thing I would say is that I can see benefits to all types of institutions, provided that you can get the like the capabilities you need, the equipment you need for the things that interest you. So if we all love doing electron microscopy, we know it's expensive. We know there's really fancy new equipment, and the older equipment is showing its age in many cases. So it's if the institute has the interest and the resources to invest in equipment, I think it's a big help for us in this community. But I think more generally, the national labs provide a really good introduction to many people. It's not like the focus on going straight into academia and tenure and how many people can I graduate in so many years. This adds a layer of stress that I think is a challenge, especially these days. So I found the pathway to National Lab User Facility to be actually really good one to go. Of course, I only did it once, so I can't really. I made my choices also based on the location. I mean, who wouldn't want to live in Berkeley? And the industrial labs I've worked in have been atypical, so large companies with very blue sky research. So I couldn't speak to other research in smaller companies, but I think that the thing I would just say is there's a lot of different career paths. And it's not the case that you have to do a straight academic career path in order to end up in academia. I think there's a lot of ways of jumping between tracks and going from one place to another.
Thank you.
Yeah.
And then I have one question here. Do you ever see defects form in your nanowires? And if so, are there any connection within the varying supersaturation in the droplets?
Oh, that's a great question. You can get plenty of defects in nanowires, and one of the best types of defects for us to study in the microscope is defects in the stacking sequence of the layers. So all these nanowires grow in close packed directions, right? So there's a 1-1-1 plane typically is the growth plane. And if you stack these close packed planes in different ways, you get different crystal structures. So for gallium arsenide, you can get wurtzite or zinc blende in your nanowire, and you can switch them with your own choice of growth parameters. You can switch between the two different crystal structures. So to me, that's the most interesting one, because it's like a deliberate thing you can do, and you can make heterostructures of wurtzite and zinc blende, which have different electronic properties. And in situ microscopy provided the clue as to the mechanism of this process of switching. So it's a great story. The other defects like twin boundaries, random defects, you can definitely see them forming, and you can try to work out what parameters of growth lead to certain defects, and to some extent you can then control them, but not with like atomic level precision, I would say. There's always some randomness, some surface like pinning point or contamination or something that could mess up the results. Yeah.